In this video, we're going to be talking about some partial derivatives. And just to give you an idea of what we're going to be looking at in this lesson, think about the area of a parallelogram. Okay, the area of the parallelogram is going to depend on the horizontal length, the other side length, and the measure of the angle kind of in between them. Right? It depends on x, y, and theta. So if I was interested in the rate of change of a with respect to x, which we denote using dA dx with those kind of curled d's, that would be how much area do I expect to add on to the parallelogram when I bump up x, right? When I'm increasing x, what is the increase in the area? Okay? And in the same way, I could talk about the rate of change of a with respect to y. And that would represent how much area are we expecting to add on when we bump up y, right? Now we could probably be a little more formal about that, right? We probably think it's the amount of area we tack on when we bump up x or y by 1 and leave everything else constant. But then there's also, what does it mean by the rate of change of a with respect to theta? Because it doesn't really make sense to think about increasing theta by 1 radian. That's just not going to be it. So what we're going to think about instead is, like what if we changed the measure of the angle? What if we made it a little bit wider, And we had, maybe I'll draw this dotted. So maybe draw it like that. Okay, if I add on delta theta, well, what's the change in area? Okay, and so dA d theta is going to be the limit of change in area divided by change in theta as change in theta goes towards 0. So that's going to be, I'm going to have to put, yeah. And so in some ways, these derivatives are going to be very similar to the derivatives we're already familiar with, but in some ways they're going to be slightly different. So let's go in and let's get an actual definition of the partial derivative. So here you'll see that the definition of the partial derivative is almost exactly the same as the definition of the derivative last year in AP Calculus, except we're going to be interested in the impact on the output variable, that f or that z or whatever, after tinkering with x just a little bit, or tinkering with y just a little bit, right? We're just adding a little bit onto x and leaving y the same, or we're adding a little bit onto y and we're leaving. But much like last year, we're going to kind of look at the definition, maybe compute a partial derivative or two using the definition, and then we're going to move on from that and just kind of take derivatives the old way. All right, so let's take the derivative of z equals x squared plus 5y. This one's going to be really easy to use the definition on. So we start with the limit definition. It's the limit of f of x plus h and y, okay, minus f of x and y. We know that f of x and y is x squared plus 5y. The only difference in those two things is that we've replaced x with x plus h, and then we subtract them and divide by h. Okay, so when I actually square x plus h, I'm going to end up with x squared 2 times x times h and an h squared. 2xh plus h squared plus 5y, and then I'm subtracting an x squared and a 5y. So those things are gone, these things are gone, and I'm dividing this by h. And so what I'm left with is the limit as h approaches 0 of, well, 2 times x times h plus h squared. Both of those have a factor of h in them. And I could kind of cancel that with the 1 power in the denominator. So I'd be taking the limit of 2x plus h as h goes to 0. Well, that's just going to be 2x. And then if I wanted to take dz dy, I'd set it up with the limit definition. So I'm taking f of x and y plus h, although I wrote h there, I meant y plus h, minus f of x and y all divided by h. Okay, so I would just need to distribute that 5 to the y and the h, so that's going to be the limit as h approaches 0, x squared plus 5y plus 5h minus x squared minus 5y. You already know how this is going to kind of play out. It's all divided by h, and 5h divided by h, well, that's 5 everywhere except for 0, which is exactly what we're interested in, right? We're interested in the limit as h approaches 0, not where h is equal to 0. So that's going to be the limit of 5, which is going to be 5. Okay. So look at this. If we think about, okay, the partial derivative of z with respect to x was 2x. And the partial derivative with respect to y was 5. Well, it looks like what we do is we're just going to take the derivative of the things that have x's in them when we're taking with respect to x and treat y as a constant. And then when we're taking the derivative with respect to y, we're going to take the derivative of all the things that have a y in them and treat x like a constant. That's exactly what we're going to do. That's how we're going to take partial derivatives the rest of the way in this course. So let's do some examples. So f of x and y is 4x plus 3y to the fifth minus x times the sine of y. And I want you to find the partial derivative with respect to x and with respect to y. Now, I need to tell you about a different notation that we oftentimes use in this class, especially when we want to take higher order partial derivatives. And that would be, okay, so fx, if you ever see somebody ask for fx, that means the partial derivative of f with respect to x. So I might just put a little note, that's the same as df dx. Okay. Fx, I'm going to take the derivative of anything involving an x, the normal way, and I treat anything with y as a constant, like a number. So the derivative of 4x with respect to x is 4, but 3y to the fifth, that's basically a constant. It's like a number. Its derivative is going to be 0. And then I'll take the derivative of x times sine of y. Well, sine of y is just a constant. And if I had 5 times x, the derivative of that would just be the 5. So in this case, the sine of y, that is my 5. So this is going to be minus the sine of y. Okay. And then fy, which is the same thing as the partial derivative of f with respect to y, that's going to be, okay, the derivative of 4x will be 0 because it's constant with respect to y, plus 15y to the 4, and then, well, now I'm taking with respect to y, so I need the derivative of sine of y is going to be cosine of y, and x is just going to be a number. Now we know that the derivative of 2 sine of t with respect to t is going to be 2 cosine t. So this would be minus x times cosine y. And this is how we take partial derivatives. Now I'm probably going to show you a couple of more examples, different things that can happen. I need to show you when does the product rule get set off and when does it not get set off, because that can be a little tricky at the beginning when you're first learning how to take a partial derivative. So what I want to do is I want to, again, take zx, the partial derivative of z with respect to x, and this is going to require the product rule because I've got e to the x, which depends on x, and cosine of xy, also depending on x. So zx is I'm going to take the derivative of e to the x, which is e to the x, and leave the cosine the same. Then I'm going to add in, leaving e to the x the same, of cosine of xy. Well, let me move that over here. Okay, the derivative of cosine of a thing is negative sine of that thing. So, and since it's negative, I might make that a negative here. Okay. And then we take the derivative of the inside, right, for the chain rule. And then we're taking with respect to x, so the derivative of x times y with respect to x is going to be just y, because x times y is like x times 5. And if we took the derivative of x times 5 with respect to x, we would get 5. It's going to be minus y e to the x sine of xy. Then I'm going to also take zy. That will be, all right, well, e to the x is a constant with respect to y. And since it's multiplied, it's going to be like a constant multiple. It's going to stay there just like it did last year. Okay. And then, but the cosine of xy, okay, we're going to take the derivative of that cosine because it's got a y in it. And I'm going to have to be multiplied by negative 1 because the derivative of cosine is negative sine. We leave the inside the same, and we multiply by the derivative of the inside. The derivative of x times y with respect to y is going to be x. All right, another one I want to show you is z equals x divided by y. This one, you would think you're going to need to use the quotient rule, but you're not. Okay, so if I'm going to take the derivative of z with respect to x, then, well, really I'm going to think of it as x times 1 over y, where 1 over y is just a constant. It's like a number. Well, then I'll just be left with that 1 over y. and then zy. Okay, well, really, I think if I'm going to do this one, I might need to write this as a negative power. So I'm going to call that x times y to the negative 1. So I'm going to use the power rule on y, and I'll get negative x y to the negative 2. And then that's it, right? There's no derivative of the inside or anything to worry about because we're taking the derivative with respect to y. Okay? Now, there is one other thing that I want to tell you about, and that's, higher order partials. So I'm just going to tell you that when we say, say fxx, what we mean is the second derivative of f with respect to x both times. But we could take the derivative of f with respect to x, get a function, and then want to take the derivative of that with respect to y. So, using the old notation, the dy dx notation, we'd say it's the second partial of f with respect to x and then with respect to y. And these are going to be, in general, two completely different things. And, actually taking these partial derivatives, it works exactly the same as what we've been doing so far in this video. And I think I would just set you off to, discover how that works. But I need to tell you about the lairaut theorem, which is also just known as the equality of mixed parts. So that theorem says that if fxy and fyx are both continuous on an open region, then they are equal on that region. Okay? And I'm just going to show you how this works based on, derivatives we've already taken here today. All right, so let's take it all the way back here. So if I have zx equaling 2x, and I wanted to take the derivative of that with respect to y, well, there's nothing that has a y in it, so that partial derivative is 0. And then over here, if zy is equal to 5, that means that zyx, taking the derivative of 5 with respect to x, I'm going to get 0. Same thing. Let's do another. All right, if I wanted to take fxy, I'd be taking the derivative of negative sine y with respect to y, and that would be negative cosine y. Whereas over here, if I took fy and took its derivative with respect to x, well, all I have that has an x in it is right here, and the derivative of a number times x is just that number, so I end up with negative cosine y. Let's do another one. Here's a good one. I could write this as y to the negative 1, and if I took the derivative of zx with respect to y, I'd get negative y to the negative 2. But if I took zy and I took its derivative with respect to x, I would get, okay, this is number times x, I'm going to get just that number. And it's the same. Okay? I could show you on the other one, but it would just, again, I'd be showing you that these things are equal, and I think that I've shown you enough times for now. Now, the last thing I want to show you in this video is how we can estimate the value of derivatives from a contour map. Okay? And so suppose this figure shows a contour map for a function f of x and y. At this point, we're only going to be able to say whether something is positive or negative or 0. But this is going to be a good skill for you to have. So df dx at point P. What I'm thinking here is I'm going to let x increase by a little bit, and I'm going to track the change in f. Right? That's really what the partial derivative is. So you think, what happens as I increase x from point P? As I increase x from point P, f goes from 2 to 3 to 4. Right? And so that means that f is increasing as x increases. So I'm going to say df dx is positive. Okay. df dy at point P is like, well, what's going to happen to the function when I let y increase by a little bit? But when I let y increase, I'm still on the same contour, still on the same level curve. Z still equals 2. So it looks to me like z is not changing when I change y, so I'm going to say this derivative is 0. Okay, at point Q, when I let x increase a little bit, I'm still on the same contour. Z has not changed. F has not changed. Its rate of change with respect to x would be 0. And then if I let y increase by a little bit, Okay, I'm going from 1 to 2 towards 3, so f is increasing as y increases, so df dy is positive. And now if I had to compare these two things that were positive, if I had like df dx at point P versus df dy at point Q, and it was like, which one's bigger? Well, at point Q, it's like, okay, I'm going up, and I'll try to leave these the same length, these arrows. Okay. When I went to the right from P, f pretty quickly increased from 2 to 3 to 4. Whereas when I'm increasing the y coordinate from point Q, f is going from 1 to 2, but it takes a while, and then it's going to eventually go to 3, but it's going to take even longer. And so I'm going to say that the rate of change, f is changing faster as you move from the right from point P than it is as you move up from point Q. So I'm going to say that inequality is going to be true. But if we had kind of a grid or some kind of scale in the x and y world, we would probably be able to more accurately approximate these things. So what I'm going to tell you is that df dx at point A, well, just kind of think of it as a rise over run situation. It's approximately equal to, it's not exactly equal to, but it's going to be approximately equal to the change in f divided by the change in x near point A. And so we can find out what that's going to be. Okay, the change in f as I go from point A to the next contour is going to be from 21 to 29. So that's 29 minus 21, an increase of 8. And then I'm going to divide by the change in x. Well, x went from 1.5 to something that I'm going to say is approximately 3.1. And then so the change in x is 3.1 minus 1.5. So that would be 8 divided by 1.6. I'm sure that's arithmetic you could do on your own. I'm just going to leave it like that. And then if I wanted to know about df dy at point A, well, let's say, well, that's not going to be exactly equal to, but it's going to be approximately equal to the change in f divided by the change in y. We can figure out what that is. Let me go from 1 to the next contour. Okay. And so as I went from point A to the next contour up, f decreased by 4. This would be 17 minus 21 is negative 4, divided by, okay, this was 1, and we're going to say that this is, I don't know, 2.2 or something. That'll do. So then y went from 1 to 2.2, and I'll get, negative 4 divided by 1.2, whatever that is. And that's how we can approximate values of partial derivatives from a contour map. And I think that's all I've got to show you about partial derivatives for today. Thanks for watching.